I'm going to talk with you today about our project classification models to prioritize static analysis alerts in C. The problem we're addressing is that static analysis of code results in too many alerts to be manually dealt with. When code bases are analyzed by static analysis tools, sets of alerts are output, and today they need to be manually examined, and that results in some being labeled true or false and many of them not being examined at all. We aim to automate handling and to automatically label most of them as true or false, and be left with a small number that need to be manually examined that can be looked at. Our approach is based on what was novel in FY16, that we developed a combined use of multiple static analysis tools, a variety of features, and competing classification techniques. In the figure, you can see that there's archived audit data that's labeled true or false, and we make two main types of classifiers with them. One that develops classifiers using all of the alerts, and another type that splits out the data, only data that's relevant to a particular coding rule or CWE or some other taxonomy item like a MISRA rule. And then we develop the classifiers using that data. And then we test a subset of that data to find how accurate those classifiers are. Now, in our work last year, we realized that there's another problem. It takes too long to audit enough alerts to develop accurate classifiers to automate the triage for many of the CWEs or other coding rules. So the approach we took this year is use an automated analysis of test suites. There are test suites that have where the programs are known to have a particular flaw or known to not have a particular flaw. So we use that information to create automatically audited, automatically labeled static analysis alert archives. Secondly, in combination with MITRE, we've systematically mapped cert rules to CWE IDs. The purpose of that is we're trying to use the test suites across taxonomies. Test suites are developed usually for one taxonomy, most often for CWEs. We wanted to use them for cert rules and eventually have the same technique enable us to use test suites for other taxonomies. Then steps 3 and 4 are done for the same reason. We modified our scale research tool. It's an auditing framework tool to integrate CWEs, to do some alert fusion, and we're going to have a DoD organization's test classifiers using this modified scale on alerts from real world code. We're going to test our classifiers built from the test suites data on this real labeled code and see how accurate our new type of classifiers are. The test suites that we used in this project are the Juliet test suite, which has about 61,000 C and C++ tests, and IARPA Stone Soup, which has about 4,600 C tests. Those are labeled with metadata that tells us where there are CWE flaws. We have metadata that tells us where there are true positives that are at the line level of granularity, and at the function level of granularity, we know where there are definitely not particular CWE flaws. Related to the intertaxonomy use of test suites, we approached a third problem, that test suites in different taxonomies need to be used. or we want to be able to use them. So our solution is a precise mapping between taxonomies, and then we partition the tests using precise mappings. Most taxonomies have some mappings to other taxonomies. For instance, a CWE 190 in both CERT's publications and in MITRE's publications showed that there was a mapping to INT31-C. What we did was make that mapping precise. We defined that set relationship and sometimes more. Sometimes we defined which functions were involved, which variable types, and so on. So we've precisely mapped all 248 CERT C rules to CWEs. Let me restate that. We made all of our CERT mappings to CWEs precise, and there were 248 of those. Then we partitioned sets of thousands of tests relatively quickly. The figure you see, the chart you see to the right shows mappings for 3 different CERT-C rules, and each row is a CWE. You can see that for some of the CWE mappings, we were able to use thousands of test suite tests, but for other mappings, there were 0 files from the test suite we could match. So we expect that the classifiers we develop for the CERT coding rules will be missing some features, even though for free, sort of, we'll have developed a lot of data for the CERT coding rule. So the way that we did this partitioning involved examining together that precise mapping. We looked at the test suite metadata, and rarely we had to actually go into the test code and examine a small bit of the code. For instance, check to see if the variable type was a float or an int, or check to see what a function name was to see how it fit into the precise mapping. So using this method in all, we've been able to identify about 2,600 stone soup tests that we can use for making CERT rule classifiers, and about 80,000 Juliet tests that we can use for CERT coding rule classifiers. And we haven't even completed the Juliet test suite partitioning using this method. 32% is left. So we've been successful at this cross-taxonomy test suite use. So this slide simply summarizes the problems and solutions that we addressed in this project and the steps of our process. This slide talks about using CWE test suites for multi-taxonomy classifiers. It's really complicated looking. The first line in blue is really the thing to focus on. One time we developed data for classifiers, and then per rule or CWE classifiers, we filter the data. And this slide also has a lot on it. I'm just gonna have you pay attention to the part boxed in red. It shows that we've developed a lot of new data for creating classifiers. We've used more static analysis tools on our test suites since this slide was made, but at this time we had only 4. And with those 4 tools, we had 22,900 automatically labeled true alerts for our data, and about 30,000 automatically labeled false alerts for our data. So we were able to develop a lot of data for developing classifiers. Similarly, this slide shows data from 4 tools per CWE. In this case, we show bars where the blue bars are false labeled alerts. The kind of orangish olive are true. And the point of this slide is to show that for the 35 CWEs, where we have data for at least 5 automatically labeled falses and 45 automatically labeled trues, It shows the mix of true and false. The significance here is to create classifiers, accurate classifiers, you need a mix of true and false. Okay, now let's talk about the actual classifiers we've developed so far. So the first data you see on the slide is information about accuracy and area under the curve of all data CWE classifiers using 4 different classification methods. The significance here is, or the accuracies here range from about 79% to 84%. So pretty okay accuracy. Our goal is still 95%, but pretty good. Now, the colorful results that you see on the slide are just the lasso classifiers, lasso logistic regression per cert rule classifiers. We had enough data to create classifiers per cert rule for 36 cert rules. The green colored ones have accuracies that are 95% or higher. Yellow are 85% to 95%, and red are below that. Now, the red ones are not necessarily too bad. Their average, in fact, are 72%. So even those were okay. And lastly, we just have room here for the lasso per CWE ID classifiers. We were able to develop 31 so far, with an average accuracy of the per CWE classifier of 82%. So the major improvement is that we were able to develop 67 per rule or CWE ID classifiers versus only 3 in FY16 when we were working with 10 years of cert auditing data and 3 DoD collaborators. So this is significant because a major obstacle to benefiting from classifiers for use with static analysis is that you need so much data to start up. So if we can get everybody started with this artificially created data, we can help people to improve their handling of static analysis alerts. So in summary, our work this year built on our last year's work. We developed a widely useful general method to use test suites across taxonomies. We developed a large archive of pre-audited alerts, developed code infrastructure that's extensible, and we're continuing our work developing classifiers and creating more data. And then in FY18 and FY19, we're going to continue this work. We're planning to make an architecture for rapid deployment of classifiers and varied system. The idea is to be able to provide code that can be plopped down in many different environments with just small scripts that need to be modified a little for environments that use particular new types of static analysis tools. And our overall goal, again, is optimal automation of static analysis, alert auditing, and other code analysis and repair. This slide shows the team that's worked with me. And does anyone have any questions? Yes.
So, are you doing any work towards taking the knowledge out of these rules and putting them back into the static analysis programs, so that instead of checking afterwards, you're getting better static analysis up front?
So this year we haven't, but that is definitely part of the proposal that's been funded for the next 2 years. So good question, and yes, I think it's very important to have a learning system.
Hi, so the curiosity for me is the transferability of this to another type of system that has noisy alerts such as security? Is there any potential for that?
So hopefully, yes. So the classifiers, are supposed to determine which features are most useful for classification, and to learn which features in particular combinations are helpful. So definitely the purpose of using the classifiers is to help to cut through the noise and not use something simpler like 60% of the time this alert is correct, so we should use that. That's an okay method to use, but there are better statistical methods.